Right. So let's take a look at how to do mole problems, which really are about converting different values like grams or liters, etc., into moles, or to do the reverse. I'll have a series of problems that I will copy from the problem set that is posted on Learning Point. Let's take a look at this first one. It says how many grams are in 1.33 mole sample of MgN2. Now what you're going to notice is the following. We're being asked to figure out how to use my stylus. That's what we're being used. Okay, we're being asked to figure out how many grams there are in 1.33 moles. Bear with me, I'm writing. It's the first time using this. So we have one step. We want to go from moles, we want to get to grams. Now what we're going to do is we're going to use what I refer to as the proportion method. This proportion method is a long way of doing problems when it comes to moles. However, it makes the ideas easier to see. So I'm going to do a few of these mole problems using the proportion method. I'm then going to switch and show you how to solve these problems using dimensional analysis. Now on exams in this class, you need to use dimensional analysis only, so the proportion is just a way to get started and understand what we're doing. So when we use the proportion method, you will notice that I have grams here. As soon as I see grams, I should recognize that I need to convert this right here, magnesium nitride. I need to know the weight that 1 mole of magnesium nitride weighs. So the first thing I will do is I will take magnesium nitride and I'm going to find out how much 1 mole of that compound weighs. And in the method that we've seen before, you would take magnesium, look it up on the periodic chart, and you would notice that its atomic mass is 24.31. And according to this compound, there is only one of them. Now nitrogen, looking up on the periodic table, nitrogen weighs 14.01. But you'll notice there are 2 of them. That's what the subscript down here means. So now what we do is we multiply this out. So 24.31 times 1 is 24.31. 14.01 times 2 is 28.02. And what we do is we now sum that up. And when we do so, we find it's 52.33. Now what this means is 1 molecule of MgN2 weighs 52.33 atomic mass units. However, if I count out a mole amount of this compound, if I count 6.02 times 10 to the 23rd of these items, it weighs the same number in grams. It was Avogadro who worked this out. Therefore, 52.33 grams is the weight of 1 mole. And that is called the molar mass of MgN2 because it's the weight of 1 mole of it. Now, Now we can solve the proportion. So we'll draw a little squiggly here, say right. So what happens is I write the proportion that 1 mole of Mg N2 is the same as 52.33 grams. Now I could have written this as 52.33 grams on top and put the 1 mole on the bottom, so the ratio works either direction. Now the issue is, but I don't have 1 mole. The problem says I have 1.33 moles. So if I have 1.33 moles of Mg N2, the question asks, how many grams is that? So that's now a proportion. Notice right here, this is called the unit ratio. It's the ratio between 1 mole of the substance, and in this case, the weight in grams that it would weigh. I now set up as a proportion because I don't have 1 mole, I have 1.33. And now what I do is I'm going to cross multiply these two items. Now the way I would set that up is as follows. I would write down 52.33 grams, and I like to use parentheses here to set it apart, and that's going to be multiplied times 1.33 moles. To save space, I'll just list it that way. Now that's going to be equal to X grams times 1 mole. Now I want to get rid of my units here. So you will notice I can cancel grams with grams. I can cancel moles with moles. And when you do that, I'm out of space here, but when you do that, you will find that 69.60 equals X grams. Now, the question is that number reasonable? That's always an important question to ask when problem solving. What I mean by that is you'll notice 1 mole weighs 52. But I have more than 1 mole. I have 1.33 moles. So you would assume that this should weigh more than 52.33, and it does. Therefore, this answer seems reasonable. Now remember, we solve this problem using a method referred to as proportions. Okay? Now how else can we solve that? I'm going to set us up with a new problem and show you a new method. Right. Now, this is the same kind of problem. And it's the same kind of problem in that I'm being asked to figure out how many moles there are in 47.5 grams. So a way to look at it is I've got 47.50 grams of a substance, and I need to convert it to a certain number of moles. Okay? Now, we're not going to use a method called proportion here. We're using a method referred to as dimensional analysis. a bit of a time my pen here. Now the dimensional analysis will achieve the same thing we saw with proportions. In this case, it's going to give me the number of moles. But we're going to use a method that is much more efficient. Let's take a look. Now dimensional analysis is in many ways just a mathematical trick. Because it's a mathematical trick, we're going to do things simply because that's the way it works. So when you have dimensional analysis of any problem, you start with the number that is given. You're given the number 47.50 grams. So here's your rule. You take the number and you write it down. Why? Because it works. So 47.50 grams of NH3. So you wrote the number down with the units. You place the number over 1 and you print parentheses around it. Why? Because that's the way you do it. It works. So you give a number, write it, over 1, parentheses. Now we're going to do a series of what is often referred to as train tracks. So what you now do is you create another blank setup where you have parentheses and you have the dividing line. Now what you do in dimensional analysis is you take the units that are on top to the left and you put those units to the right down below. So I have grams of NH3. Now here's what we got to do. If I have grams showing up, I need to find out the molar mass of ammonia. So what I do is I come down here and I write correct, NH3. Nitrogen weighs 14.01. I have one of them. Hydrogen weighs 1.01. There are 3 of them. Therefore, I get 14.01. I get 3.03. 4, 0, 7. I get 17. Now, checking my own calculation here. There we go. So, what happens is this. This is the weight in grams of 1 mole of the NH3. So again, this is your molar mass. Let's come out here. You'll notice I have grams of NH3. So what I do is I put 17.4 grams of NH3, look at that, is 1 mole. Of NH3. So I can now cancel this with this. Now, what am I looking for? I'm looking for moles. Do I have moles? I do. So now what I do is I simply multiply across. I get 47.5 times 1 mole. So it's 47.5 moles of NH3 divided by 17 point, my bad, 04. That was an error. This should be O. So, if I have 47.5 divided by 17, I get 2.8 moles of NH3. That's my answer. Does this seem reasonable? Well, I have 47.5 grams of NH3. 1 mole of NH3 weighs 17. I have 47. I must have more than 1 mole, and I do. I have 2.8 moles. So, that looks pretty good. Now notice, I've gone from grams to moles. We refer to that as a one-step problem because I simply went from weight to moles. What other kind of problem can I have? Let's take a look at that. Right. This is a new problem. What volume is occupied by 53.25 grams sample of Cl2 gas? Okay, now we're given the weight. We're being asked volume. So what we see is I've got 53.25 grams. Now, what I have to do is I have to figure out how many moles there are in 53.25 grams. Once I know how many moles I have, I can then convert those moles into liters of Cl2 gas. Make that L a little better there. So this is a two-step problem. I have to take grams to moles, and then I got to take moles to liters. So I have a two-step process here. Now we're going to use the method now of dimensional analysis. Now, one thing we're going to notice right away is I have mass going on here. I have weight. Now, because I have mass, I have to find the molar mass of the chlorine. So the first thing I'm going to do is I'm going to find how much chlorine weighs. So chlorine, if I look it up on the periodic table, chlorine weighs 35.45. I got used to writing with this, I'll tell you that. But I have two of them. So when I multiply them together, I wind up with 53.25 grams. That's not right. My scratch work is not correct. 35.43 times 2 equals, there we go. It equals 70.86. Now, what does that number mean? It means if I measure out 70.86 grams of Cl2, I have 1 mole of Cl2 molecules. So now I come back here, I say, right, I know how many grams of this I have. By the way, you'll notice I don't have 70.86, I have 53.25. So I need to convert 53.25 grams to tell me how many moles. Now let's think about that. 70.86 grams is 1 mole. I have 53.25. So I clearly have to have less than 1 mole. So here's your setup. When you do dimensional analysis, first rule, whatever number they give you, put the number down over here. So we put down 53.25 grams, get that correct if I can, of Cl2. You put it over 1. Why? Because that's what you do. It's shortcut and it works. What you then do is create another one. Now, we're going from grams to moles. So we say, right, so here's how we approach this. We're going to put grams of Cl2 down here. Why do I put grams of Cl2? Because I want to cancel the grams of Cl2. Well, what grams of Cl2? 70.86 grams. Now, why would I choose to put the grams here? Because I want to put moles on top. This is a unit ratio. 1 mole Cl2 over 70.86 grams. That's the unit ratio. So this is the amount that I'm given. I'm multiplying times this. But wait, I'm not looking for moles. I'm looking for liters. So I have to have a second step here. I need to take moles to liters. So here's what I do. I come back to my dimensional analysis. I create another train track. Since I have moles of Cl2 on top, I'm going to put moles Cl2 on the bottom. So 1 mole of CO2, I'm going to liters, so 1 mole of Cl2 is the same as 22.4 liters of Cl2. So notice, I want to get to liters. I have liters on top. So now what I do is I can cancel. Grams of Cl2 cancels grams of Cl2. Moles of Cl2 cancels moles of CO2. I'm left on top liters of CO2, which is what I want. So now what I do is I multiply what I have in the numerator. When I get this, it's a really weird number. It's 1,192.8 liters of Cl2 divided by what's on the denominator, 70, did it again, 0.8. Now, when I do the calculation here, I get 33.66 liters of Cl2. And that is my answer. Now, as always, is that a reasonable answer? Well, first of all, I was given grams. I wanted to know how many liters that was. I've got it in liters, so I'm good to go. I also realize that 53.25 is a smaller mass than 70. So I have less I did a calculation error. Interesting. Right, I have a calculation error. 1192.8 divided by 70 is not 33.66. Instead, oh, it shows up in black, really? Well, I'm learning all kinds of things on this first round. So the answer here is actually supposed to be 16 point, wow, 85. So 16.85 liters of Cl is the correct answer. Very poorly written. Here's why this number makes sense. It's actually a nice illustration of what we were just doing. If I've got 53.25 grams, that's smaller than 70. Therefore, I have less than 1 mole. 22.4 liters is 1 mole. My answer should be less than 22.4 liters. My original number was clearly not, and that's why I knew, whoa, something's wrong. It has to be less than 22.4, and in fact now it is very poorly written, but now it is 16.85 liters of Cl2, and that is the correct answer. So finally, take a look. This is called a two-step. It's weight to moles, and then the second step is moles back to liter. We use dimensional analysis, where we place the weight here over 1, parentheses, create another parentheses. You take the units on top, create the same units on the bottom, but you're going to use the unit ratio 70 over 1 over 70, and then cross cancel again. We multiply across the numerator, we multiply across the denominator. We don't do the same mistake Mr. Kurth did and do the wrong math. You wind up with the answer. And that is how you do that. Let's do another one. Okay, here's another problem. This problem says how many grams are in 33.55 times 10 to the 18th molecules. And that's the molecule you're working with. As soon as I see the word grams, I know at some point I need to know the weight of 1 mole worth of this material. In other words, I need to have the unit ratios. So the first thing we're going to do here is we're going to calculate the mass of 1 mole of that. So our strategy is N H4 H2 PO4. Now I'm going to write down N 14.01. I have one of them. Hydrogen. This is interesting. The molecule is listed as split. But the reason I'm doing it is it's showing you that's a polyatomic and that's the other polyatomic. When it comes to hydrogens, though, you just sum them up. So 4, 5, 6. So it's 1.01 times 6. Phosphate is going to be equal to 30.97 times 1. Finally, oxygen is equal to 16 times, and there's 4 of them. When you carry out that math, what you find is 115.04 grams is how much 1 mole of this molecule weighs. Okay, now we're going to tuck that away because we're going to use that information coming up. Let's go back to the problem and say, right, we have a certain number of items. 10 to the 8, 3.55 times 10 to the 18th. What we want to do is we have to convert that to moles, to the number of items that are in there. And then say, right, if we know how many items we have or how many moles we have, we can now solve for the weight. Once again, it's a two-step problem. Why are we doing all of this? We're doing this because when you solve reactions in chemistry, we have to be able to convert to moles, and from moles convert to other values. So this is a conversion process. We're going to use dimensional analysis for this, of course. Let me shift down to here so we make it fit. So when you do dimensional analysis, your first move is take the number of molecules that you have. So 3.55 times 10 to the 18th. And you always want to include the units. That is the number of items that you have. You always place that first number over 1. Why? Because it works. You put it in parentheses. Why? Because it works. You set up your next parentheses. Sometimes you refer to this as a train track. I'm not quite sure why they call it that, but there you go. So now what happens is this. You'll notice there's a number here. So I'm going to give myself some more space. So I'm going to don't give myself space then. I'm going to just continue with what I'm doing. So I'm going to have the following. This is the number of items. So I need a number of items down here. So 6.02 times 10 to the 23rd, that many items is 1 mole's worth of this molecule. But you'll notice this ratio gives me how many moles. But I want to know how many grams there are. So now what I do is I set up another train track. I say, right, 1 mole of NH4 H2. So 1 mole of it weighs, we know right here, 115.04 grams. So 115.04 grams is 1 mole of items. So the number here cancels the number here. The moles here cancels the moles there. And we're left with grams. Now a question sometimes comes up. The question is this: why not put 1 mole on top and put 115.04 down below? In other words, can't I flip this ratio? Yes, you can, absolutely. However, I want to wind up with grams. So I want gram on top in this unit ratio, so it gets me to where I want to go. That's how I made that decision. Now when you multiply this out, you get the following, and I would like to show you how to do this. So bear with me here. You're going to multiply 3.55 times 10 to the 18th times 115. Let me write that again up here. I'm just going to show you the math of this. 3.55 times 10 to the 18th. You're multiplying that times, right over here, 115.04. So what you do is you multiply this number times 3.55. What do you do with this? You do nothing. You simply copy it down again after you've done that. So when you carry that out, you wind up with 408. That doesn't belong there. Let me see if I can make the eraser work this time. No guarantees on this. Nope. Shoot. Brilliant. Sorry. Let me see if I can correct this. Okay. So, it's 408 times 10 to the 18th. Notice that's right here. Divided by 6.02 times 10 to the 23rd. Now what you do is the following. You take this portion right here, 408 divided by 6.02. When you punch that in the calculator, you get 67.81. So you take these two values and do a regular division. What do I do with these exponents? You take 18 minus the 23, and that will give you 10 to the minus 5th. And that is your answer. 67.8 times 10 to the minus 5th grams. Now, is that a reasonable number? Well, 6.02 times 10 to the 23rd is 1 mole. This is a much smaller number. So I would expect the weight of this to be much less than the molar mass. The molar mass is 115 grams. This is telling me I have 67 times 10 to the minus 5th grams. Wow, that's a small number. That makes sense. It's a much lighter setup than before. Okay, Last one. How many liters are occupied by 4.35 times 10 to the 20th molecules of O2? So let's again, what are we being asked to do? We know there's a certain number of molecules of O2. We need to convert that to moles. Then we need to convert that to liters. So we have a two-step mole problem. Convert the number of items you've got to moles, and then the number of moles you've got to liters. Notice, nowhere do you see grams or weight. Therefore, I don't need to solve for the molar mass. What do you mean by that, Mr. Kurth? Means you do not have to go O2, O equals 16 times blah, blah, blah. You do not need to do that because you don't need any kind of mass conversions. So we're going to do a dimensional analysis to make these conversions. What's the rule? Take the number you are given. So the number is 4.35 times 10 to the 20th. That's the number of molecules of O2. Place it over 1. Why? Because it works. Put it in parentheses. Set up another set of parentheses. Why? Because it works. Okay, now, think it through. I have a certain number of items here. I'm trying to convert to moles. Well, what I do know is 6.02 times 10 to the 23rd number of molecules is 1 mole. That's a unit ratio. 1 mole is this many items. So notice the number of items cancels with the number of items. Am I done? No, I have moles here. I now know moles. I want to get to liters. So set up another train track. So 1 mole of O2 is 22.4 liters of O2. My moles cancel moles, and now I have liters, which is what I want. Once again, could I have put 1 mole on top over 22.4 liters on the bottom? Could I have done that? Absolutely. That is valid. But now I can't cancel my moles up here to down here, because down here I have liters. I don't want that. And I would have moles on top, which means my answer is moles. I don't want moles. I want liters. So I choose to make my ratio set up in this manner to get me where I want to go, which is liters. So what do I do now? So what I do now is I'm going to multiply 22.4 times this number, and I'm just going to tack on the 20. So let's see if I get this right this time. 22.4 times 4.35, that's going to give me 97.44, and all I do is just take the exponent, the power of 10, take it 10 to the 20th. My units are liters. That's all going to be over 6.02 times 10 to the 23rd. So what do I do now? I take these two numbers, 97.44, divide it by 6.02, and that gives me 16.19 times, I take this exponent minus that exponent, it gets me 10 to the minus third liters of O2 gas. And that's how you do these conversions. Done.